We're going to go over now the second example in your related rates notes on page 18. So for this example, you have a cylindrical tank has a radius of 3 meters and a depth of 10 meters. It's being filled at a rate of 5 meters cubed per minute. How fast is the surface rising? So first let's sketch our picture. We always do so with the given information and a cylinder with a radius of 3 meters. And anytime we are doing a related rates problem, we want to think of the scenario in terms of time passing and whether or not the unit of measure is changing with respect to time. So when we're filling a cylindrical tank, the radius isn't changing, it stays constant at 3 meters. While as the water rises, we can see that the height of the water level is going to change with respect to time. And also pay attention to the units of measures. Here we're given meters cubed per minute. So when it says the tank is being filled at a rate of 5 meters cubed per minute, we know that this is the rate of change of the volume with respect to time. So we're going to want our know, want, and relate columns. What we know is, and we can jot down things that are in the diagram. The radius is 3 meters. I am for now going to write fixed here just to make a note of that so that eventually I will use that information in my relate column. The depth of my cylinder is my height, and that is 10. And height is not fixed based off of the water level rising. And we also are given dV dt. The volume is changing at 5 meters cubed per minute. When I go back to the question for my wants, I'm asked for how fast is the surface rising. So how fast the surface is rising is with respect to time, how the height is changing with respect to time. So that is dH dt. And since they didn't say at any particular moment in time, I'll just leave it at that, dH dt. And when we write our relate, we're going to think of how we're going to relate these units of measures like 3 for the radius, height with volume. And that's going to come in the volume formula for a cylinder. The volume formula for a cylinder is pi r squared. The circle is the base of a cylinder, and we have h number of circles, or think of like the height as how many circles we have that we're adding together. And this idea is going to come into play when we get to integration. But for now, the formula that we remember is pi r squared, the area of the base times the height. And so when I go to fill in the problem further, I'm going to consider things like, well, the radius is fixed. So when I'm thinking about how things are changing, how the quantities are changing with respect to time, the radius isn't changing at all. So I'm going to go ahead and plug that value into R, and I'll highlight that here. Okay, so in my next step, I'm going to put that 3, let's plug that in here, times h, and we can rewrite that as 9 pi h. And now the formula for volume that we have is V equals 9 pi h. At this point, because we want dH dt and we're given dV dt, we can take the derivative implicitly. So the derivative of V is dV dt, remember with respect to a third parameter of time, equals 9 is a constant, pi is a constant, and h is to the first power. So this is just a simple power rule. 9 pi times, because we took the derivative of h, we're going to multiply by dH dt. And so our unknown, what we're trying to solve for here is dH dt. And we know what dV dt is. Also pay attention to the fact that dV dt is positive 5. And the reason for it being positive 5 is that we're filling the water, so the volume is growing. So sign does matter as well when we're considering the rate of change. So we have here dV dt is 5, 9 pi times dH dt. So solving for dH dt, we get dH dt equals 5/9 pi. And the unit of measure would be meters per minute.